harmonic series is the following sum of numbers: 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. This is an infinite series which does not converge to a finite sum. There are many things to explore with this series in a calculus class, but in this video we are going to explore where its name comes from and what it has to do with sound and music. The partial sums in the series form a sequence of numbers called the harmonic numbers. For example, the first harmonic number is 1, the second harmonic number is 1 plus 1/2, which is 3/2, the third harmonic number is 1 plus 1/2 plus 1/3, which is 11/6, etc. These harmonic numbers are related to the harmonic mean. You are familiar with the arithmetic mean of a set of numbers, which is found by adding the numbers up and dividing by the amount of numbers you added, but the harmonic mean is the reciprocal of the arithmetic mean of the reciprocals of a set of numbers. That's a bit more complicated, so let's just look at an example. Consider the two numbers 1 and 1/3. Their reciprocals are 1 and 3 respectively. The arithmetic mean of those reciprocals is 1 plus 3 divided by 2, which is 2. And the reciprocal of that result is 1/2, which is the harmonic mean of the numbers 1 and 1/3. Putting it all together, the harmonic mean of 1 and 1/3 is 1 divided by the fraction 1 over 1 plus 3 over 1 divided by 2, which is equal to 2/4, which is equal to 1/2. From this example, we see another interesting fact. Each number in the harmonic series is the harmonic mean of the two numbers adjacent to it. So as another example, 1/3 is the harmonic mean of 1/2 and 1/4. 1/4 is the harmonic mean of 1/3 and 1/5, and so forth. The numbers in the harmonic series relate to the harmonics that appear naturally in vibrating mediums, like strings, columns of air, and stretched membranes. When these mediums vibrate, there is a fundamental tone, called the first harmonic, and there are overtones which have frequencies equal to integer multiples of the fundamental frequency. For example, if we play an A on a piano with fundamental frequency 110 Hz, there will be overtone harmonics with frequencies 220, 330, 440, 550, etc. But these overtones will have lower amplitudes or volumes. Frequency is related to period length by the use of a reciprocal. So a frequency that is twice as much as the fundamental completes one period in 1/2 of the period length of the fundamental. We can visualize the fundamental and these period lengths with the harmonics with this image from Wikipedia. Different instruments have different amplitudes for the overtones, which gives them their own character. We can visualize the differences in the harmonics and compare two different instruments playing the same note on a spectrum analyzer. The first sound is a piano playing an A at 220 Hz. And the second sound is a clarinet playing the same note at 220 Hz. The clarinet is interesting because it emphasizes the low-frequency odd harmonics. This is why a square wave on a synthesizer, which only has odd harmonics, is a good sound source to synthesize a wind instrument like a clarinet. On the other hand, the saw wave on a synthesizer has all harmonics, which makes it a good sound source to synthesize a variety of instruments. There is one wave on the synthesizer that only has the fundamental and no overtones, the sine wave. If we take a fundamental sine wave and then add sine waves representing the harmonics, we can build a sound to mimic other instruments. This is called additive synthesis. The pipe organ is one instrument that can do this, but the first electronic instruments that used additive synthesis were built using the tone wheel as a sound source. A tone wheel is a spinning disc with ridges that creates a sine wave, and if we add more tone wheels or different sets of ridges to one wheel, we can produce the harmonic overtones for a fundamental. The first electronic instrument to use the tone wheel was the telharmonium, of which there are no recordings since only 3 were made. However, this technology found its way to the Hammond organ, which has found its way into many recordings in the last 100 years. The Hammond organ has drawbars that add harmonics to the fundamental, which is the third drawbar. Then the fourth bar is the second harmonic, the fifth bar is the third harmonic, the sixth bar is the fourth harmonic, the seventh bar is the fifth harmonic, the eighth bar is the sixth harmonic, and the ninth bar is the eighth harmonic. The first and second drawbars give sub-octaves below the fundamental and third harmonic. If we extend all of the drawbars and play just one note on the Hammond organ, we get an audio representation of the sum of 9 of the harmonics represented in the harmonic series. An even more extreme example of this is the Harmonic Synthesizer module from Make Noise. Using the harmonic output, I can add 24 partials, meaning 24 harmonics, to the fundamental or tonic center. The Harmonic Series is in almost all music we hear, since almost all instruments produce sounds with the fundamental and harmonics. But here's an interesting use of the Harmonic Series as a sound effect.
Coca-Cola Pop and Pour.